That's Taylor's remainder theorem and Taylor's inequality. All right. So, well, of course, when we are yes.
Oh, sorry, just a quick question. For the one we're doing right now, so we wouldn't have to complete the integration. Just give the.
Yeah, I guess. Well, yeah, you would have to do it, but the most important here was to find the number of terms. The rest is just, evaluate and simplify. So, and well, actually, yes, good question. According to my result for the previous example, this should be, yes, thank you. That's equal to 0.0615538. All right, so that's the value of the integral. So for Taylor's remainder theorem and Taylor's inequality, well, so this is like, well, the good topic to wrap up the entire chapter about infinite sequences and series and power series. This is basically the purpose of all of it, So, well, because for example, in the previous example, we use an approximation for x e to the negative x. Because we're using an approximation, well, that means we have some error, right? There's some room for error. And well, it depends on how many terms we use, which in the end gives us a good result, an accurate result, or maybe a poorly done approximation. And well, for example, let me think of this. Let's think of this with numbers. 1/3. How much is that equal to? When you think of 1/3. 0.3. Let's talk about 0.33. All right. Typically, a third it's 33%. It's an approximation, right? However, in this case, because we are approximating, that means we have some remainder. Same if we approximate 1/3 to be 0.333. Even if you have this many threes, of course, there's still some remainder, all right? There's some remainder. Of course, the second result is more accurate than the first result, right? Due to the number of decimals that we're using, but still, the remainder is larger on the first example, but on the second, it's a more refined result. So the same happens with polynomials. So for example, a function f of x for which we expand a Taylor polynomial or a Maclaurin polynomial, and that's going to depend on whether the center of the expansion is at 0 or if it's at some value a. That's what makes a difference between Taylor and Maclaurin. For example, these expansions have whatever Taylor expansion is if we use, for example, just 5 terms, 7 terms, and the remainder. All right? Now, what happens? Okay, this limit expression right here is telling us that the limit of using infinitely many terms make the remainder equal 0. Right? So that's the whole thing about an infinite series. That if we use all the infinitely many terms, we have no remainder. That's the actual result. All right? And well, so for example, so in a similar way that we did before with the numbers, so if we have e to the x, okay, we know we have this polynomial expansion, 1 plus x squared over 2 factorial plus x cubed over 3 factorial and some remainder. And well, that remainder is, putting some symbols here. Okay, so this is t sub 3 of x, because this is the Taylor, well, let's just call it Taylor in general, even though it's centered at 0. It's centered at 0, and that should be technically Maclaurin, but let's call it Taylor, okay, for the sake of simplicity. Well, so if this is T3, well, then we will have a remainder Rn, or not Rn, actually, the remainder of using only the third degree polynomial expansion. Likewise, e to the x, again, that's also 1 plus x squared over 2 factorial plus x cubed over 3 factorial. What I'm going to do is just add more terms. Nothing really interesting. So x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus some remainder. In this case, for example, we are using T6, the Taylor expansion of 6th degree, and well, we're going to have the remainder of using the 6th degree expansion. That is, that'll be terms of 7th degree and on, right? And well, of course, depending on how many terms we use, we're going to have, of course, a better approximation. And you know what? Just to give you the picture, let me go back to section. What was that? Okay. So think of this example. Let's take it back to section 11.1. Okay, let me erase all this. It's not working. Yes, all right. So for example, in this case, what do we have? We have the exponential function with the first degree of Taylor expansion, or the linear approximation. Now, suppose that we want to know what the error will be if within the range, say from -1 to 1, all right? Okay, so around 0, okay, if you look at some values around 0, we're going to have pretty good approximations. But because of this linear approximation is not very accurate with the curvature of the exponential function, so very quickly these two graphs are going to start to diverge, right? So we wouldn't be able to use this linear approximation to, for example, approximate e to the first power, because look at the difference between the actual value and the approximated value, right? Now, let's look at the same for the quadratic approximation. So we want to study the approximations between -1 and 1. Now that second approximation, which is the second degree approximation, it's starting to get some curvature here, and it's starting to look like the exponential function. I mean, for some limited values. I mean, more values than the linear version, than the linear approximation for sure. But in this case, well, I mean, as we get close to the bounds, well, that difference between the actual and the approximate, I mean, there's still some difference, but that difference is less in comparison with the linear approximation. Now let's observe the cubic one and see how the gap starts to get closer, you know? And what about with the quartic approximation? They're pretty much the same, right? Between -1 and 1. So in this case, well, there is some maximum error at the endpoints right here, but in this case on the linear is more evident than in the quadratic, than it is on the cubic and on the quartic, and so on and so forth. I mean, Of course, the whole thing stems from the fact that, I mean, if we write infinitely many terms in the polynomial, well, which is not a feasible task, of course. But I mean, of course, that's why we're talking about approximations. All right, let me go back to 11.4. All right, so we were here, but now the question is, how do we find that maximum error? Well, so we have this inequality right here with some values where the remainder is less than or equal to the value of the next term in a very similar way that in the alternating series test. And well, so we need to find a polynomial approximation first, and then and then we're going to apply this inequality. I'm going to show you how to use this inequality. So first of all, let's do one example. So let's approximate the function f of x. And by the way, there's a little typo here. The function that we're supposed to work with is the cube root of x and not the square root. All right? So, well, in a very similar way that we analyze the exponential function with different expansions, linear, quadratic, cubic, and quartic, within the interval -1 to 1, which is 1 unit away from its center, 0 in this case. Well, so we are going to find a Taylor polynomial of degree 2. Well, it's just a degree 2, centered at 8. And then we're going to analyze what happens within the interval 7 and 9, which is 1 unit away from the center, which is 8. So let's start by finding the series first. So f of x, okay, that's the cube root of x, which will be x to the 1/3, all right? And well, f evaluated at 8, that's the cube root of 8, which equals to 2. Let's take the derivative, and that's going to be 1/3 x to the -2/3 when we subtract 1. And this is the same as 1/3 x to the 2/3. And then evaluate the first derivative at 8. This will be, okay, 1/3 times 8 to the 2/3. Okay, this 8 to the 2/3 first. Let's evaluate that one first. Okay, the denominator 3 really tells us about the index of the radical, which is the cube root. Well, the cube root of 8, which is 2, and that 2 being squared, that's going to give us a 4. And that times 3, that's going to give us a 1/12 in the denominator. All right? In other words, so in case you want to see this more in detail, this is the same as saying 3 cube root of 8 squared. But instead of squaring the number, that's a cube root of 8, quantity squared, cube root of 8, which is 2 squared, which is 4 times 3, that's 112. That's where this quantity is coming from. All right? Let's go with the second derivative, and yes, well, we don't need to find too many derivatives here, which is great. So that's going to be -2/9 x to the -5/3, which is -2/9 x to the 5/3. And then from here, evaluate the second derivative at 8. That's -2/9 times 8 to the 5/3. All right, so evaluating the quantity in the denominator. So again, 8 to the 5/3 is the same as saying the cube root of 8, and then raise to the 5th power that number. So the cube root of 8, which again is 2, and then to the 5th power, which is 32, and then 32 times 9, that's Hmm?
288.
288, which reduces to 1 over 144. All right? And yes, negative. Thank you. And well, I'm going to take one more derivative because again, well, I'm not going to evaluate at the derivative at that value. Only we're going to need this third derivative because we need it for the Taylor's inequality in this case. So what are we going to do here? Number one, okay, so negative times a negative is positive. 2 times 5, which is 10. 9 times 3, that's a 27. X to the negative 8 thirds. All right, which is the same as saying 10 over 27 x to the 8 thirds. So let's form our Taylor polynomial first. So t, in this case, it's t sub 2. Because they were asking us only for the Taylor series of degree 2. All right, so this will be on the one hand, well, number one, let's do the notation first. F of 8 plus f prime of 8 times x minus 8 to the first over 1 factorial. If you want to write this as over 0 factorial, that's fine. Otherwise, that's fine. And f double prime evaluated at 8, x minus 8 squared over 2 factorial. Well, as we did in the previous lectures, all we need is to identify these values right here, which come from here. All right? Just plug them in where they correspond. And this will be t sub 2 of x equals 2 plus f prime of 8, that was 1/12, x minus 8 to the first power, and then minus 1 over 144 x minus 8 squared over 2 factorial. But 2 factorial is the same as saying 2 and then dividing 1 over 144 dividing by 2 is the same as multiplying the two numbers in the denominator. Isn't it true? Okay, so let me then fix this instead. So that's going to be 1 over 288. All right? So that's our t sub 2. All right? This means this is approximately the cube root of x using only the second degree polynomial. All right. So we got the longest part. So now we need to set up the inequality, Taylor's inequality, which tells us that, well, the remainder r sub n of x, the absolute value of that, and I will explain why it's an absolute value in this case in a second. Well, m over n plus 1 factorial times the absolute value of x minus a raised to the n plus 1. And well, in this case, well, what is that value of m? This value of m depends from the previous page. Okay, let me go back to the previous page. So this value of m in the form of an inequality is obtained from evaluating the following derivative that we used on the Taylor expansion. For example, for this exercise right here, we used the second degree polynomial. So that's why I took the third derivative, because that's the one that we're going to use to evaluate and find that maximum bound. Well, here is the thing, because this notation right here might be a little bit funky because we have a lot of symbols, a lot of letters, absolute value. Okay, number one, before continuing with this, for example, when you see this, x less than or equal to 3. Okay, what comes to your mind when you read this when you read this statement? Anything. What's the first thing that comes to your mind?
The value has to be less than 3.
All the values that are less than 3 but also equal to 3, right? Well, maybe you would picture this on a number line. Okay, this is 0, 1, 2, 3, and all the numbers below 3 and equal to 3, right? That's the set. And then we can shade, of course. All right. But I mean, another way to say this is, because this is a set of numbers, isn't it? It contains infinitely many numbers, all the numbers from negative infinity up to positive 3. Another way to say this is that, and it's important to have this mindset right here, is that this set has a maximum value of 3, right? And for example, if I reverse inequality to x greater than or equal 3, okay, yes, we will have this picture, but the other way around, pointing the graph pointing to the right in this case. But in words, how would you describe this inequality here?
Has a minimum value of 3.
It has a minimum value of 3, right? So that's something that we need to understand when it comes to inequalities, so we can get the picture of what we're going to do. All right? Because this is, for example, this is of the form x less than or equal, all this garbage, you can just call it x. Do we all agree with this? This is some sort of x less than or equal some value a. All right, that means that this value right here has to be the largest or the smallest. What would you say about it?
The largest.
The largest, right? The largest. So in this case, we need to split this calculation into 2 parts. All right. We need to do a calculation for m, and we need to do a calculation for this as well. Let's do one at a time. So in this case, okay, let me do the one in green first. I think that one is the easiest one. So recall that we're doing this. So we have this graph right here, center at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 8 right here. And we have some graph right here. And we are approximating this with, okay, that's 8, with something like this, right? It's centered. No, it didn't come out the way I wanted. Okay, perfect. So this is going to look like this and like that. Notice at 8 we have the actual value, the accurate value, but 1 unit below. Do you see the gap right here? Okay, let me zoom it in. So there's a little gap right here, and 1 unit above, well, it's not visible, but there's also a little gap in there, right? Okay, so the picture here is, well, if we want to evaluate if we want to use the second degree approximation to approximate values at a neighborhood around 8, well, we're going to have some error. But if we wanted to say, instead of having it from 7 to 9, well, how about from 6 to 10? From 6 to 10, do you see how the gap starts getting bigger? Well, so that's going to be a different maximum value. All right, but in this case, we're interested in the one between 7 and 9. All right. Of course, we're going to analyze this picture again once we're done with this. And well, so you need to think of these two expressions right here. So number 1, x minus a to the n plus 1. In this case, well, n, because n is 2, because we're using the second degree approximation, and the center A is at 8, absolute value of x minus 8 to the 2 to the 2 plus 1, that is x minus 8, absolute value of that, to the third power. And then in this case, we need to evaluate that absolute value expression on both endpoints 7 and 9. All right, x equals 7 and x equals to 9. And find, in this case, the largest of them, because again, we want to make sure that the quantity on the right-hand side of the inequality is as large as possible. So, well, absolute value of 7 minus 8 cubed, and absolute value of 7, no, not 7, it's 9 minus 8 cubed. All right. Well, in both cases, it happens to be simply 1. All right. So in this case, we just figured out the factor that we highlighted in green. That should be a 1. That's all it is. Of course, if we were looking at a wider neighborhood of values, in this case, instead of 7 to 9, say from, okay, so 8 minus 3 is 5, 8 plus 3, from 5 to 11, well, that number is going to differ. It's going to be different, and that's going to make a larger value. And if you if you think of the picture, well, that means the gap is increasing because we are expanding our interval to places where the gap between the actual value are really bigger from, or differ really big from, the approximated value. Now, the next one might be the trickiest one. Well, m. For m, we need to, let me write down that part of the inequality. That's the absolute value of the n plus 1 derivative less than or equal, just less than m. And we're going to find that value of m by evaluating the third derivative. Remember how when we were obtaining the third derivative, we didn't use it to put it in the polynomial. We use it to evaluate and find m. So we need to find m. Now, here is the thing. So the third derivative, which is 10 over 27 x to the 8 thirds, we have two options. We can evaluate this, number 1, at x equals to 7 or at x equals to 9. In this case, well, we need to pay special attention at, okay, evaluating at which value 7 or 9, between 7 or 9 is going to make this m the largest possible. 7. Do we all agree with 7? Well, this is because, well, if we evaluate at 9, we're going to produce a larger number in the denominator, and we're going to get a smaller number. But otherwise, if we evaluate it at 7, we should obtain a smaller number in the denominator, getting, in this case, the largest possible value. All right, so let's evaluate only, so that's going to be 10 over 27, 7 to the 8th thirds. All right, and now that we have, okay, I'm not going to compute this yet. I'm going to go back to, okay, this is, nope. I'm going to highlight instead. Okay, this will correspond to that value over here, and this will correspond to that value highlighted over here. I'm going to go back to the setup of the inequality right here, r sub n. So absolute value Rn is less than or equal, okay, m, which is 10 over 27 times 7 to the 8th thirds divided by n plus 1 factorial, but in this case our n is 2 plus 1 is 3 factorial, and then that times the quantity in green, which happened to be simply 1. Alright, so this means R sub n, x less than or equal, so that's going to be essentially 10 over 27. Okay, let me do 27 times 7 to the 8th thirds under 10, and that times the 3 factorial. And while simplifying this in the graphing calculator, it's going to give us 0.0034. All right. What does that number represent? Yes?
So when we plugged in the x minus 8 to n plus 1, would you choose, let's say the values are different, would you choose the smallest number or the largest?
The largest. For both we need the largest. Yeah. So well, what does that value represent anyway? Okay, let's go back to the picture. That means that at the very edges of this interval for which we want to do the estimation, well, this means that at the gap right here between the approximated and the actual is of an error of 0.0034 or 0.34%, which is a pretty good approximation despite being only a second degree approximation. So that's the whole thing that's what I think it summarizes everything about approximations using this polynomial series. What are the implications? Okay, how can we make this a lot better? All right, let's say you're working on a project, and the project, for whatever reason, the situation on your project is modeled by one of these polynomial approximations, but you want to obtain better results. And well, you would say, well, 0.34%, well, let's make this error even smaller. What would be a good idea to improve this error? What would you do? There's a couple of things that we can do to improve this error. Maybe add more terms to the series, one more term or two more terms, or maybe restrict. The other way is to restrict the interval. Instead of having it from 7 to 8, maybe from 7.5 to 7.5 to no. Oh, it was 7 to 9. Yeah, 7 to 9. Yeah, so that means 7.5 to 8.5, right? Maybe tighten the interval for the permitted interval in this case, just narrowing the neighborhood of values for which this approximation will be. All right, and this actually wraps up all chapter 11.